Are you tempted to use an enum in your design? Before you do, consider whether you might use a flyweight pattern instead. This seems to me to be one of the less well-known patterns, and it's not one I feel is particularly well explained in the Gang of Four book. In this video, we're going to take a look at the comparison between enum and flyweight. We'll consider the relative benefits, and we'll dive into an example implementation. Enums have lots of benefits when used in the right place. Let's review them first. One of them is type safety. Imagine you're creating a poker program and you want to represent the suit of a particular card: hearts, diamonds, clubs, and spades. One simple approach would be to use an integer so that, for example, 1 represents hearts through 4 to represent spades. But this has a problem. If you write a function that expects to get a suit as an argument, what will it do if the value is one of the 4 billion or so other integers that aren't 1, 2, 3, or 4? One possibility, of course, is to include range checking in the functions, but that's messy and, worse, would potentially have to be duplicated in every piece of code that uses a suit in a computation. An enum suit is a type in its own right, and that lets the compiler verify that we're not passing arbitrary values into our suit handling functions. The next feature that an enum gives us is essential to completing this notion. The enum source code defines all the objects that will ever exist at runtime, assigning them to variables, well, constants really, so we can refer to them by meaningful names: hearts, diamonds, clubs, and spades. Part of this depends on the fact that the enum type prohibits any new instances from being created at runtime. In Java, this means that enum constructors are always private. The type is more or less final. This is actually subtler than that, but we can never extend an enum. And the serialization mechanism is modified so that it will never create a new object of the type, but will instead find the existing object that matches what's being deserialized. Because we can't create new objects, but only have the predefined ones, referred to by their field names, they're actually public static final fields, we can also use the double equals operator to test if two expressions refer to equivalent values. If they do, then, unlike, for example, strings, they absolutely must be referring to the same object. In Java, an enum is a fully fledged class, subject to the above constraints, but we can give them methods and fields, both static and instance, and more. Take some care with instance fields. Remember, there's a fixed number of instances, and each instance is pretty close to a global value. Values that get mutated from a piece of code that's a long way, in code space or time, from where you're looking can be surprising. And surprising is a euphemism for a bug waiting to happen. Enums might be safer used in a form that has them entirely immutable, but that's not an absolute rule. So, enums are wonderful. Why might we want anything else? Well, there are a couple of things about enums that might not always be wonderfully convenient. First, you actually have to know and be able to name the values at compile time. You might wonder why you wouldn't know this. More on that in just a moment. Second, the number of instances is fixed, and you cannot add more instances at runtime. Wait, that was the whole point, right? Well, yes, but consider this example. Imagine you're writing a registration system for a school. You've been told that the school offers courses in mathematics, physics, chemistry, and 7 other topics. Great! There are 10 courses. Let's use an enum. Now, in this case, it's surely preferable to have a type specific to the notion of course rather than just use a string. We don't want to register someone for Nerdlesprocket by accident. That's not a course, but it is a valid string, right? It's also not hard to imagine course being an immutable type, such that we create a single object, mathematics, and then use it again and again. After all, if the type is immutable, then any mathematics is equivalent to any other mathematics, and creating thousands of objects is a huge waste of memory, and requires equivalence comparison to be done by checking the individual fields for equivalence, which is computationally slow, rather than checking object identity. Now, enums handle both of these concerns, but you can probably see where I'm going. It's not long after you've deployed this system that you discover that one of the professors wants to add a new course to the catalog. And that's a problem with enums. If you want to add a new one, you have to recompile the code and restart the server. So, enter the Flyweight pattern. You might call this a dynamic enum. The pattern will give us a type-safe representation and ensure that any two references that refer to equivalent objects actually refer to the same object, allowing us to use identity-based comparison. That's the double equals operator in Java. So how can we do this? Well, one of the first things to notice is that we cannot allow our new type to expose a constructor. If you call new in Java, you either get a brand new object of exactly the specified type, or you get an exception. In our case, we'll need to expose a factory type behavior such that we can call it twice with equivalent arguments and get a reference to the first created object on the second and subsequent calls. This, in turn, means we need to keep track of all the objects of this type we create, and do so in a way that lets us find out if an already created object matches the current request, so we can return it directly rather than making a new one. There are, of course, several approaches to this problem, but one pretty simple one illustrates the idea. And what I mean by pretty simple one is that you might like to think about whether something better is possible in your particular situation. This one's not a disaster by any means, but there might well be more efficient ways of going about this. We're going to use a map to store all the objects we've created. The key to the map will be a simple string representation of the course parameters. The value will be the created object that matches those parameters. If we get a request for an object based on values we've already seen, we'll find the object and return it directly. Here's the basic structure of the course class. The class is final for the same reason an enum is. If you can subtype a class, you can change pretty much anything about it and break the rules that it attempts to enforce. There are two fields, one for the name of the course and the other for the professor who teaches it. These are final because we want this class to create immutable data. That's not entirely necessary for this concept, but if you can change the contents of one particular course, what are the consequences to all the other parts of the system that have a reference to the same object? It might be fine, but it needs careful thought. The constructor is private. We need complete control over how and when objects of this type are created. The initialization is simple enough, though. Now we get to the heart of this pattern. We're going to keep track of all the objects that we create. They will be the values in this static map. The keys in this example will be a string composed from the names of the course and the teacher. So if we get two requests for a course called Underwater Basket Weaving, taught by Albert Einstein, we end up with the same object for both requests. The factory method is called of. The name is not a syntax thing, but it's common in Java's APIs for factories to have this name in the absence of anything compellingly more expressive. The unique identification for our course is made by concatenating the course and teacher's names. This is something where you might well find a better approach in a given situation. But however you do it, there must be a one-to-one correspondence between the key you generate and the identity of the resulting object. Next, we look to see if we've created an object already based on the factory parameters. If we haven't, then we'll make a new object and add this to our store, ready for another request for an equivalent object. Finally, we return the object, whether it's a new one or one from our store. We'll give this a toString because we should. Well, okay, seriously, we want to be able to look at these things and see what's happening. But we won't need to create equals or hash code. The inherited behaviors that we get from java.lang.object will be just fine. Now, we need to exercise this. We'll build a main method, and we'll have 3 references, 2 of which will refer to equivalent objects. Now, what happens if we compare the object identities of the first and second? Well, they're different objects, which is good since they have different contents. But if we compare the first and third, we have that enum-like behavior, so we ended up with the same object reference, and the double equals comparison returns true. If we request hash codes from these objects, the value from math1 and math3 are the same. It's not really surprising since they're actually references to the same object. But meanwhile, math2 gives us a different hash code value, which is what's desirable for objects that do not compare as equal. What about the dot equals method? This, if not overridden, delegates to the doubles equals comparison, so it should be no surprise that this works too. This is a pretty simple pattern. Although this implementation is illustrative and could likely be improved for many real examples, particularly when it comes to generating the unique key for a given set of field values, there are some other considerations we should think about. First, if we made this class serializable, notice this one isn't, we'd ruin the validity of object identity comparison. Deserializing an object by default creates a new object. You can and should fix that if you need serialization in this type. Second, it's clear that the code for an enum is far simpler than this. I don't think this code is particularly tiresome, but if you don't need the ability to add new items at runtime, the extra work of this pattern is probably wasted. Another thing that troubles me is that Java's record feature seems to invite this kind of approach. It's meant to be an unmodifiable data carrier, and in that case, 2 record instances with identical field values could potentially benefit from pooling and the identity-based comparison that this offers. But you can't easily make a record with a private constructor. There's more to this discussion, but the requirement that record constructors cannot be less accessible than the type itself is certainly inconvenient here. I admit I don't quite understand why that decision was made, though I'm sure there was a good reason. Now, so far in this discussion, I've emphasized the enum-like features of this pattern, suggesting that we might occasionally want to add a new value at runtime. But as a reminder, there is another category of use cases for this that are worth calling out again before I wrap up. So for illustration, let's suppose we're passing an XML file of customer records into an in-memory tree structure, and for whatever reason we're not simply using the provided libraries for that structure. We might have a huge number of node objects representing less than, customer, greater than, and the other tags. Now, even if there are attributes associated with these, we might still have a great many equivalent values. If we allow every one of these nodes to be a separate object, we might run into memory issues. If instead we use this Flyweight pattern, we can ensure that all equivalent nodes are represented by a single object, potentially saving a vast amount of memory. Now remember, no design approach is right for every situation. You must consider the specifics of what you're trying to do, and perhaps how it might change over time. But the Flyweight is often overlooked, and a simple enum type isn't always the best tool when you first think of it either.